Hi guys, and welcome to your Unit 10 Lesson 1 notes. In this unit, we will be learning all about radical expressions. Before we can learn about radical expressions, we first need to talk about what radicals are, and in doing so, we'll take a look at all of the real numbers. Now, by the end of the day, you'll be able to describe the relationships among sets of numbers. When we talk about numbers in this class, we're talking about real numbers. There's another kind of numbers that are called imaginary numbers, but we will not be talking about them. If you want to come by and ask about them, you can, but we won't be covering them in this video. So real numbers are not imaginary numbers. Now, there are a whole bunch of types of real numbers. Most people, when they think of numbers, they think about the natural numbers. So the natural numbers are numbers like 1, 2, 3, 4, 5, 6, 7, 8, 100,000, things like that. These are numbers that we count with, so we call them the counting numbers. So we use n to represent the natural numbers. That was really messy. The natural numbers. We use n because n for natural. The natural numbers. Our next set of numbers include, let's see, what color do I want? I want this color. In addition to our natural numbers, if we add 0, then we call those the whole numbers. So whole numbers are numbers like 0, 1, 2, 3, 4, stuff. So whole numbers are 0 and the natural numbers. So our next set is the whole numbers. These are our counting numbers, our natural numbers, and 0. Our next set of numbers includes not only 0, 1, 2, and 3, but also -1, -2, -3, etc. So we call those guys, those are basically, your counting numbers, 0, and your negatives. We call those guys integers. So the integers are all whole numbers, all the natural numbers, and negative numbers. So other integers include, -7 and -8, but also, 40 and 8 and numbers like that. So we have our next set of numbers. It's called the integers. Now I know what you're thinking. You're thinking, Miss Van Dyke, why don't we use I for integers? Why do we use Z? Well, I is used for, some people like to use I for irrational or for imaginary numbers or for an ideal group. So I don't like to use I. In fact, it's very common to use the letter Z because this comes from the German Ganze, I'm probably pronouncing it wrong, but Ganzezahlen. That's German for whole numbers. So when mathematicians talk about integers, they use Z because it's German. Isn't that fun? I'm usually giving you guys Spanish facts, but now you get a German fact. So that's exciting. Again, our integers are our counting numbers, also 0, but also negative numbers, negative whole numbers, that is. Our next set of numbers are numbers like 1/2, -3/4, 0.28, and -0.3333333333. We call these guys rational numbers. Rational numbers are represented by Q. And I'll explain why in just a little bit. So rational numbers are all numbers that can be expressed in a fraction form. they look like A over B. And fractions are all quotients, so that's where the Q comes from, because they are all written as quotients. They're all written like a fraction. So all fractions will have a repeating decimal. All rational numbers will have a repeating decimal. This is because anything that can be written in a fraction can be written as a repeating decimal. Examples of repeating decimals are things like, 0.22222, like we saw, that's the same thing as 2/9. Or 0.5, because it's got 0.5000 at the end, that 0 repeats, that's the same thing as 1/2. So those are rational numbers. Now those are nice numbers. You can think about them the right way. You have rational numbers. Now please notice that when you have a rational number, anything that's inside of the Venn diagram is also counting as a rational number. So 7 is an integer. It's also a rational number because it can be written as 7/1. That's a fraction, so that works, right? Same thing with our natural numbers. All natural numbers are whole numbers, and all whole numbers are integers, and all integers are rational numbers. So they nest inside of each other. This is almost all of the numbers that we will ever deal with, but there's one more kind. This is a kind of number that is what is not rational, also known as irrational. So our irrational numbers are numbers that can't be rational. So they're numbers that aren't written as a fraction. For example, the square root of 2 can't be written as a fraction. You just leave it like that. Or pi has a decimal approximation. It's 3.141592653, right? But it can't be written as a fraction. It just keeps going. Or you could have, something like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10, 0.11, 0.12. You can figure out the pattern, but it's not going to be a repeating decimal because it's not the same thing over and over and over again. So those are irrational numbers. They cannot be written as a fraction. We use P because it's a nod to Pythagoras, like your Pythagorean triangle, to represent the irrational numbers. So irrational numbers are numbers that are not rational. Therefore, they cannot be written they cannot be written in a fraction form, and they have non-repeating decimals. Cool? Cool. Now that we have all types of our real numbers out here, let's go ahead and classify what kinds of numbers these are. We start out with 3. Go ahead and look at your Venn diagram and find out, where does 3 fit? Well, 3 is a natural number because it's a counting number. Because all natural numbers are whole numbers, it's also a whole number. Because all whole numbers are integers, 3 is an integer, and all integers are rational numbers. Therefore, 3 is all of these guys. 3 is not irrational because it can be written as a fraction is equal to 3/1. So that works. Let's look at the square root of 24. The square root of 24 cannot be written as a fraction. Therefore, it is just plain old irrational. Let's look at 5/20. Oh, yuck. First of all, we can simplify that. How do we simplify 5/20? Well, 5 is equal to 5 times 1, and 20 is equal to 5 times 4. So these 5s are going to cancel out, giving us 1/4. Now 1/4 is not a natural number because we can't count with it. It's not a whole number because it's not a counting number and it's not 0. It's not even an integer because it's not like, a whole solid number, positive or negative. However, it is a rational number because it can be written as a fraction. Awesome. So it is just rational. Now finally, let's look at the negative square root of 16. The square root of 16 is 4, so the negative square root of 16 is negative 4. Now negative 4 is not a counting number. It's not a whole number because it's not a natural number or 0, but it is an integer. That's good. Now remember that all integers are rational numbers. Negative 4 is rational because we can write it as negative 4 over 1. And because it is rational, it is not irrational. You did it. We have classified all of our numbers. Now sometimes when we don't know exactly what a number is, we can still approximate it by rounding and then putting it on a number line. So I'm going to show you those 2 ways to approximate a number. First, let's approximate the square root of 24. I feel like we just talked about this. Okay, so the square root of 24, if I plug that into my calculator, that'll give me something like 4.89. Now that actually does round up to 4.9. I asked for the nearest tenth. So 4.9 is what we'll go with. It's approximately 4.9. We can also estimate it by putting it on a number line. So if I draw a number line, I know I'm going to want to put the square root of 24 between 2 other numbers, and I'm going to look for perfect squares. 24 is between 2 squares of 25 and 16. Now 16 has a square root because the square root of 16 is 4, and the square root of 25 is 5. That's going to be super helpful later. We're going to want to keep these guys in mind. Now, if we want to put the square root of 24 on here, that's going to be closer to 25. So if we put that here, then we know the square root of 24 goes right here. And that would make sense because 4.9 is closer to 5 than it is to 4. So here we have it. 2 ways to approximate this is an irrational number. The square root of 24 is approximately 4.9, lies right there. Let's do another one. This time we're going to work with a negative number. The square root of negative 11. Well, if I want to put that on a number line, I want to look for other squares, perfect squares. Well, the square root of the negative square root of 16. 16 is a perfect square. We also have a negative square root of 9 because 9 is a perfect square as well. Now 11 is closer to 9. It's going to be about there. So the square root of negative 11 is going to be about right here. Now the square root of negative 16, the negative square root of 16 is negative 4. The negative square root of 9 is negative 3. So that tells us that the negative square root of 11 is going to be between negative 4 and negative 3. And that does make sense because the square root of negative 11 turns out to be negative 3.3, approximately. Alrighty, now we're going to determine if each number is rational or irrational. If it is irrational, we're going to find 2 consecutive integers, like we just did above, that it lies between on the number line. Let's recap real quick. Remember, rational means it can be written as a fraction, and irrational means it's not written as a fraction. Cool. Let's test it out. So, the negative square root of 30. Well, 30 is not a perfect square. What are some perfect squares around 30? We've got the negative square root of 36, and then the next one is 25. So the negative square root of 25. If we want to have the negative square root of 30, that's going to be between the negative square roots of 36 and of 25. So that guy's going to go, let's do pink, right here, negative square root of 30, because 30 is between the squares 36 and 25. Now, the negative square root of 36 is negative 6, and the negative square root of 25 is negative 5. So we know that the negative square root of 30 is going to be between negative 6 and negative 5. So we can write that as the negative square root of 30 is between negative 6 and negative 5. Let's do one. Oh, we didn't mark it as irrational. It is irrational. It's irrational because it doesn't come out to an integer. Now let's look at 36. Hey, we just talked about 36. 36 is a perfect square, which means the square root of 36 is 6. And 6 is a rational number because it can be written as a fraction. It can be written as 6 over 1, or it can be written as 12 over 2, or it can be written as 60 over 10. Each of these is proof that 6 is a rational number because rational numbers are written as fractions. Ta-da! So there you have it. We've classified numbers as rational or as irrational. If we have an irrational number, we can say what numbers it's between, and we can determine what groups, what sets our numbers belong to. You will want to save this image for your archives. It will come in super duper handy later. I hope you enjoy the rest of your homework.